Okay, folks, I want to introduce to you Professor Philip Stark. He's a professor of statistics at the University of California at Berkeley and is a former member of the Board of Advisors of the EAC. I want to tell you a little story before I tell you more about him and his work. He entered the field of election integrity almost by accident about 18 years ago. Secretary Bowen, whom you heard earlier today, appointed the post-elections audit standards working group. PSWEG was the name of it, and I was chairman of that group. And one of the things that I thought we needed was we need a statistician in this group. If somebody's going to study auditing, we need a statistician. So I got the names of two statisticians at Berkeley, and the first guy couldn't do it. I didn't know either of them. The second guy was Philip Stark. I called him up, and he agreed to join our working group. And I'm afraid that call ruined his life, because for the next 18 years, he has spent a huge fraction of his time on the work that's an outgrowth of that working group. He's devoted this huge fraction of his time and research energy to creating the intellectual and mathematical foundations of risk limiting audits and evidence-based elections. Besides the mathematical theory, he's traveled the country simplifying and refining and elaborating RLA techniques, educating election officials, running RLA trials, testifying as an expert witness, particularly in the Curling v. Raffensperger trial in Georgia, and rarely has a new field, been so completely dominated by really one person. He's created the field almost single-handedly. He's got a lot of co-authors, but he's been the intellectual leader of the whole subject matter. Because, of course, I made that one cold call that brought him into this, I like to take credit for all of his life's work, so you're welcome. But as you know, risk limiting audits has now been recognized as the gold standard for auditing techniques and for securing otherwise insecure elections. So please welcome Professor Philip Stark.
Thank you so much. Thank you for the generous introduction and for making that phone call. And thank you, Secretary Bowen, for convening the PSWIG, without which, yeah, I certainly wouldn't be here. So, as David said, I've worked with a bunch of people over the years on various pieces of this. These are just people maybe in the last 4-ish years. There's more earlier. Ron spoke about evidence-based elections, and risk-limiting audits are, I think, an important ingredient in that, and I'll talk about this a bit more. But the first paper was with David Wagner, computer scientist from Berkeley, who was also part of the top-to-bottom review. And the notion, as Ron called out, is that it shouldn't be enough to just announce who won. You should also have to present convincing evidence that that person or those people won. That kind of idea was reprised a few years ago with Andrew Appel. So, what are some desirable security properties for voting systems? So one is what Ron mentioned earlier today, the strong software independence or strong software independence, the idea that an undetected fault with the software shouldn't cause an undetectable change in the electoral outcome, and strong ads, and if it does cause a change, you should be able to correct the outcome without rerunning the election from scratch. Some head scratching over that definition led to some new definitions with Andrew Appel and Rich DeMillo, contestability, defensibility. So one of the issues with software independence is, what does it mean to detect something? Who gets to detect? What happens if you detect? And things like that. Is there a penalty for false alarms if you say that there's a problem but there isn't? So the idea of contestability is that if someone observes the voting system misbehaving, they should be able to present public evidence that they observe misbehavior. And typically things like ballot marking devices don't provide that public evidence. So they fail the contestability. Even though a voter might in principle detect a problem, there's no way to convince anybody else that they did. Defensibility is the flip side, that if the outcome is correct despite what might have gone wrong, the election official ought to be able to present convincing public evidence that the outcome is right despite whatever failed. All right, so it's fine to use computers in elections where failures won't prevent people from voting. And Secretary Bowen was saying just a few minutes ago that that's an issue around things like e-poll books, that if e-poll books fail, you can stop voting. If you have universal use ballot marking devices and you're required to use them to mark your ballot, then technology failure will prevent people from voting. If you have hand-marked paper ballots, maybe you have to wait to scan them, but at least people can keep voting while that's happening. So, but the other criterion is that if you're going to use electronic equipment, if you're going to use computers in voting, you need to be able to make an end run around whatever it is they're doing and verify that they did the right thing, at least that they worked well enough. And kind of a materiality threshold for well enough is that you got the right winners. You named the right winners at the end of the day. The outcome is correct. All right, so the ability to detect problems isn't enough. You actually need looking for the problems and doing the right thing if you find them. All right, so what's a risk limiting audit? It's any procedure that limits the risk that you will certify an incorrect electoral outcome. What do I mean by risk? Well, risk is the largest chance that the outcome will be certified if it is in fact wrong. It's sort of a contest by contest decision. There's no like random generation of contests, some of which are right or some of which are wrong. It's if it's wrong, you have a big chance of fixing it. They will, with high probability, correct wrong outcomes, and they will never make a right outcome wrong. And the idea behind an RLA, as Ron mentioned, behind all of these things is to leverage the trustworthiness of the vote record in a well-run election to be able to provide affirmative evidence that the reported winners really won, or to correct the results if the reported winners didn't really win before those results are certified and become final. One of the things that RLAs are not is a way to retroactively make a poorly run election trustworthy. And I'm seeing increasingly election officials sprinkling magic RLA dust on a poorly run election and claiming that they've scienced the shit out of the election and now you can trust it. And you can't. It's garbage in, garbage out. These are the first two papers on RLAs. They were direct outgrowths of the work for Secretary Bowen on the Peace Wig. The first came out so the committee was in 2007. First paper came out in 2008, and then the first paper implementing them, trying them in a pilot contest, was also in 2009. And the author list there is kind of fun. The first three authors, Joe Hall, who many of you probably know. Luke Meritrix was at that time a PhD student at Berkeley, and me, and we're kind of the technical people, and everybody else on that paper is an election official. So this was all very much collaboration with election officials to make this stuff work on the ground. All right, so the origin was in this post-election audit standards working group. The question was, can audits somehow protect elections that rely on vulnerable technology? At the time, there were the statutory audits typically, if a state had them at all, they required examining a fixed percentage of batches, like precincts, retabulating some or all contests in those precincts, and then checking to see whether that agreed with the machine tabulation of the votes in those precincts. There are other states that had even weaker rules than that. For example, Colorado would just assemble a group of 500 ballots from somewhere, run it through the equipment, count it by hand, and see whether you got the right answer for that group of 500 ballots. There are many states that had no audits at all. These audits were supposed to answer the question, are the machines working properly? I find that a problematic question because what does properly mean? It's not a binary thing, right? There's always going to be some error rate. There's always going to be some failures. The question isn't, are they working properly? It's, did they work well enough in this election to find out who really won, right? And that I think is a better question. At the time, the computer scientists on the scene were formulating audits in a much more principled way. There was a detection paradigm. That was sort of state of the art circa 2007. That said the audit should have a large chance of you should audit enough so that the audit has a large chance of finding at least one mistake if the reported electoral outcome is wrong. The problem is that if you audit any reasonable number of batches or ballots, you will find at least one mistake, especially if they're hand-marked paper ballots, because voters mark ballots in ways that the machines can't read. So it's sort of not enough to detect. You need to know, okay, there's a problem. How big is it, right? Did it cause the outcome to be wrong? And the affirmative evidence paradigm, which started with RLAs in roughly 2007, was, has the audit given strong evidence that the reported winners really won? If not, collect more evidence or do a full hand count to find out who really won. It obviously needs to be a careful full hand count. Now, I talk about trustworthy paper trail, trustworthy record. What does trustworthy mean? It means that if you counted it completely and accurately, it would show who really won. What does really won mean? I don't know. I mean, okay, there's an infinite regression here, stack of turtles. Some vote records are born untrustworthy. They're malleable, or there's some vulnerable technology between the voter and the vote record, for example, ballot marking devices or the internet or something like that. But even if you construct a trustworthy record like a hand-marked paper ballot where voters can make mistakes, but you can't hack their pens, right? Whereas ballot marking devices you can hack, so you can in some sense hack the paper trail. So to keep the vote record trustworthy, you need physical inventories, demonstrably secure chain of custody, physical security, you need audits of eligibility, you need ballot accounting, you need a lot of things that some states do pretty well and some states don't do. All right, one of the important things you need for risk limiting audits to work is a trustworthy upper bound on how many cards were cast in each contest. So a weak but still useful upper bound is registered voters. A much better bound is participation records. If you have a good independent record of how many voters eligible to vote in this contest in fact showed up, you have a pretty good upper bound on the number of cards that were cast in that contest. All right. So Ron also mentioned this report that he was one of the co-authors of. In 2018, the National Academies of Science, Engineering, and Medicine reviewed the state of elections in the US, and their first recommendation was use paper ballots, and the second was to do risk limiting audits. So I was very happy about that. There have been a bunch of audits now in a bunch of states. There's laws in about 15 states. Not all the laws are very good. There are risk limiting audit methods for plurality, multi-winner plurality, supermajority, proportional. I mean, pretty much everything you can think of, all scoring rules. What there aren't good methods for yet is single transferable vote, which is sort of a multi-winner ranked choice voting. There are some special cases with small number of candidates. There's my colleagues from Australia, Michelle Blom, Vanessa Teague, Peter Stuckey have come up with methods for that. This is just a quick scan of the front pages of what I consider to be the current state of the art. There's about half a dozen papers here. Things have actually, believe it or not, there's been progress in 18 years, and some of the methods that people think of as the way to do risk limiting audits are really quite obsolete, both in terms of their flexibility and their efficiency and the complexity of the software you need to run them. So I'm going to talk a little bit more about the first paper here, the sets of half-average nulls generate risk-limiting audits. The conference this was at the Shangri-La Hotel, so I kind of had to do that. And explain how this is sort of a unifying way to audit pretty much all of those social choice functions that I mentioned. It reduces them all to the same underlying question. That question can then be answered using this alpha method, which basically amounts to betting. Here we are in Las Vegas, and I'm going to try to explain to you how to audit elections by betting. So that's going to be a little math lesson. You can go to sleep now or wait until I start talking about that. This none such paper, I think I mentioned earlier in response to someone's question, that lets you do the most efficient auditing method even in situations where printing identifiers on ballots might compromise voter privacy. And it lets you use untrusted technology both to imprint the ballots with identifiers and to retrieve the ballots that have been selected for audit. It does both of those things in such a way that if the technology misbehaves, it can't undermine the audit. If the outcome is wrong, you still have the same high probability of catching that and correcting it. This overstate net equivalent, I'll also explain a little bit about that, but it addresses some of the other problems that Ron mentioned, including auditing heterogeneous voting systems where you have cast vote records for some cards, but you only have batch level subtotals for others, or something like that. So there's a way to address that that makes everything a special case of one underlying thing. You can do IRV. This aware paper is interesting because it involves betting in a way that you're sort of learning the odds of the game as you go along. It's very adaptive and quite efficient for auditing RLAs. And one of the biggest improvements in efficiency actually comes from targeting the sample so that you sample enough from each of the contests that you're trying to audit without sampling just from all ballots indiscriminately. So the ability to focus the sample on the contests under audit makes it practical to audit every contest in an election, even in a large county that has hundreds of contests going on in a given election. So in this particular example, which is, these numbers are coming from Orange County, which is third largest jurisdiction in California, maybe sixth largest in the country, if I recall correctly. They had 181 contests in 2020. They could all have been audited to a risk limit of 5%. By looking at 0.65% of the cards cast, so less than 1% of the cards cast. Without using that method, you would have basically had to do a full hand count of all, 3 million cards cast. Same experiment for 2022. They had 214 contests in that election, and you would have had to count every ballot if you used a less refined method, but by using this targeted sampling, you could have done it with 3.1%, and that included 3 contests that had margins below 0.1%. The other included some tied contests, which means you're basically doing a full hand count. So that's including those full hand counts of the smaller contests. So I would like, one of the take-home messages is it's actually practical to do this for every contest in every election at this point. All right. So I'm about to do what I would advise anybody else not to do, which is give a talk that has some math for a general audience. I want to try to convince you that the nut here, the way that this stuff actually works, is conceptually much simpler than you might think. I'm not going to talk about null hypotheses or t-tests or any stuff like that. I'm going to talk about gambling, and I am going to take you through some roughly 9th or 10th grade algebra at one point. So we'll see how people's algebra goes. All right, so here's the idea. We're going to start with a bankroll of $1. We're imagining for the moment that we have a 2-candidate plurality contest, Alice versus Bob, and Alice is reported to have won. By the way, Ron once told me that he feels his most important contribution to cryptography was Alice and Bob. But so we're going to start with a bankroll of $1, and we're going to bet on, we're going to pull a ballot at random. We're going to bet on what that ballot is going to show. The rules of the game are you can bet up to however much money you have, but you can't make a bet you can't cover. You can't go into debt. If you go broke, you're out of the game. If the card shows a vote for Alice, you win your bet back, right? You double your money. If the card shows a vote for Bob, you lose whatever you bet. And if the card shows a vote for Carol or a non-vote or anything else, no money changes hands. You get your money back. Okay, this is the auditing game, right? So if by playing this game, I can win a fair amount of money by playing this game repeatedly, that's pretty strong evidence that Alice really won, all right? And in fact, that can be quantified and was quantified in a 1939 paper that I'll show in a second. All right, so if Alice beat Bob, you're going to expect to win on average more than you lose. If it was tied, you're going to expect to roughly break even, give or take, the randomness of things. And if Bob beat Alice, it's a money pump in the wrong direction. You'll eventually go broke. All right, so this 1939 paper by Jeanville shows basically that if you're playing that game and Alice didn't win, if Alice did not get more votes than Bob, the chance that you will ever multiply your initial bankroll by a factor of k is at most 1 over k. Chance you'll ever multiply it by 10 is at most 1 over 10, 10%. Chance you'll ever multiply it by 100 is at most 1 over 100, 1%. Okay? So if by playing that game, I can end up with $100 in my pocket, either Alice really won or something really unlikely happened. That's strong evidence that Alice really beat Bob. Okay? That's it. That's the statistics in all of this now. That's the way the state of the art works. That's what that alpha paper is about. That's all the statistics you need to know to understand RLAs. Okay, now let's see if we can tie this to the rest of the picture. All right, so the idea is I'm going to place bet. I'm going to do a bunch of gambling games in parallel, betting on what the next ballot is going to show. If I can make money in all of the games that I'm playing, that basically means that the reported winners really won. But I need to tell you a little bit more about how to set up those games and how to audit other social choice functions and other things. All right, so let's think about a multi-winner plurality contest. So you get to vote for up to 5 people, and the 5 people who get the most votes wins, and everybody else lost. So what we're going to do is set up a game like this for every winner against every loser. So if we had, Alice and Bob versus Carol and who's D? I don't remember who. Anyway, right? Then if Alice and Bob were the reported winners, each of them would be paired with each of the reported losers, et cetera. You'd have 4 things to look at. So you play the games in parallel, starting with $1 in each, and if you get to $20, you get up by $20 in every game, you can stop. And that's strong evidence that all the winners really beat all the losers. If you've seen every ballot, you now know what the right answer is. You can basically have tallied them. You could have tabulated the votes while you were looking at them. If you get bored at some point because it's taking too long, you can just stop and cut to the chase and do a full hand count. If you go broke, you have to do a full hand count. That's the other rule, right? If you lose your money, you got to do a full hand count. All right. So if you do a full hand count, or if you've seen every ballot, the correct answer, according to this careful manual inspection of the ballots, replaces the reported result. Otherwise, you stick with it. So this is a risk limiting audit at a 5% risk limit for a multi-winner plurality contest. Right? Problem solved. How do we do this for other social choice functions? How do we make this more efficient? This is the analog of what Ron was saying was a ballot polling audit, but it turns out that exactly the same ideas and exactly the same mathematics apply to card-level comparison audits, batch-level comparison audits, all of these things. You just need to translate the arithmetic a little bit, but the same underlying principle is if you can make a bunch of money betting that the losers really lost, betting that the winners really won, that's strong evidence that the winners really won. So you have to bet in such a way that if any of the winners didn't really win, at least one of the games is an unfavorable game, right? Is at best fair or unfavorable. Okay, so how do we make the move to the general case that lets us audit other social choice functions, that lets us think about comparison audits, not just ballot polling audits? And basically the idea is we're just going to replace votes with numbers. And the way that we replace the votes with numbers is going to depend on the social choice function. It's going to depend on whether we are doing a comparison audit or not. But the simplest case would be plurality contest. And we're going to look at one winner versus one loser, but there may be other people in that contest as well. So I'm going to encode votes with numbers. And so this idea is this first, this first ballot has a vote for Alice. I'm going to encode that vote by the number 1. Second ballot has a vote for Bob. I'm going to encode that by 0. Third one has a vote for Carol. Right now I'm trying to see whether Alice beat Bob, so Carol is going to get a value of ½ a neutral value. Lizard people gets a value of ½ They don't, right? So Alice gets a 1, Bob gets a 0, anything else gets a ½ All right? So if Alice got more votes than Bob, the average of that list will be bigger than a ½ right? There'll be more 1s than 0s, and everything else will be a ½ So the average will be bigger than a ½ So if I can show that the average of this list is bigger than a ½ by sampling from it without knowing the whole list, if I have strong evidence of that, I have strong evidence that Alice really beat Bob. So far, so good? Yeah.
Why isn't the vote for Bob a negative one? You lost it already.
It could be. I could change the scale of everything. But right now, the way this is set up is if you think of it as the percentage of votes that are for Alice, then a half is 50, yeah, okay. But you could certainly do it on a different scale. Okay. All right, so that's how it would look for comparing Alice to Bob, but we can also compare Alice to Carol, right? And we would encode votes in the analogous way. So a vote for Alice would get encoded 1, a vote for Carol gets 0, and a vote for Bob or an invalid vote gets a half. And again, Alice got more votes than Carol if the average of that list, the resulting list, is bigger than a half, right? So far, so good? Okay. So in this multi-winner plurality, we get a list for each winner, reported winner, reported loser pair, and the game is we pull a ballot at random, and we update our fortunes in all of the games that we're playing based on what that ballot shows, right? So if that shows a vote for Alice, we're gonna, we've won some money in every game that involves Alice as a winner. If it shows a vote for Bob, we break even in, we get our money back in that, but we lose money in this, right? So we're playing all these in parallel. Think of it as a multi-armed bandit, right? You're pulling a slot and anyway, all right. Okay, so if all the averages are bigger than a half, Alice really beat Bob and Carol, and the reported outcome is right. And this idea of replacing the votes with lists of numbers, encoding the votes as list of numbers, lets you use exactly the same approach to audit all of these other social choice functions. Supermajority, D'Hondt, these are like proportional representation schemes, star voting, instant runoff voting, and so on. And for all of them, it's the case that there's a way of encoding the votes as numbers so that the average of the list of numbers is bigger than a half. If the averages of a bunch of lists of numbers are all bigger than a half, the reported winner must have run. The reported winners must have won. All right, so I'm going to make this slightly more abstract. So I'm going to bet B on what the next number drawn at random from this list is going to be. I'm using the capital X to denote what the number is on the ballot that I'm going to see at random. So it's unknown until I draw it. It's a number X. The payoff is going to be I get twice what I bet times whatever number that card shows minus a half. What is this? Where did this come from? Why did I make this up? All right, okay. So let's think about how this plays out for the list of numbers that we just made for Alice versus Bob, right? So if the card has a vote for Alice, that means X was 1. X minus a half is a half. 2B times X minus a half is B. You get the amount you bet back, right? This is just a way of writing in symbols that you get your money back. You get your money doubled, right? If the card is for Alice. If the card is a vote for Bob, Bob is encoded by 0, so you get X minus a half is minus a half, twice times this minus a half is minus B. So you lose your bet, you lose all your money, right? So far so good. And if it has a vote for Carol or a non-vote, that was encoded as a half minus a half is 0, no money changes hands. So this is just a way of writing in symbols exactly what we were describing in words before, okay? Now, it turns out that if the average of the list of numbers is less than a half, this same way of encoding things works even if the numbers are not just 0, 1, and a half. It can be an arbitrary list of numbers between 0 and 1, including fractions, including whatever you like. In the same approach, you only expect to make money if the average is bigger than a half. All right? So that lets you then do some other things. All right, the game, this betting game where you bet and that's your payoff, that payoff is twice B times X minus a half, that is a favorable game only if Alice got more votes than everybody else. It's a fair game if Alice is tied with Bob, and it's unfavorable if Bob won. So you'll lose money on average if Bob won, and the chance that you get to a large multiple of your initial stake is at most 1 over that multiple, unless Alice really got more votes than Bob. All right? So if you play this game and you end up multiplying your initial stake by 20, that only has a 5% chance of happening unless Alice really beat Bob. And so that's moderately strong evidence that Alice really did beat Bob if that happens. Okay. And this point I just made, this is just, again, this works for any list of numbers between 0 and 1. They don't have to be just the numbers 0, 1/2, and 1. All right, so suppose the game is favorable. Suppose Alice really did get more votes than Bob. How should you bet, right? You're not locked into any particular betting scheme. You want to grow your fortune as rapidly as possible. That minimizes the sample size. It means you have to look at fewer ballots before you've multiplied your initial stake by 20 and can stop, right? So what are the clever ways to bet here? So the fastest way you could get to 20 is in 5 draws. If you basically double, if you bet all of your money every time, and every time you got a ballot that showed a vote for Alice, you'd be done after drawing 5 times. But unless the election was a landslide and all of the votes were cast for Alice, there's some chance you'd go broke before that 5th bet, right? Because you lose all your money and then you're over and you have to do a full hand count. So it's not very good strategy to bet the bank on each of these draws. You want to keep something in reserve in case you lose that bet, right? So you live to bet again. Otherwise you're in trouble. Okay, so how should we do it? So something optimal is going to be something less than your whole bankroll. The closer the game is to a sure thing, that is, the larger the majority for Alice, the safer it is to bet more of your stake each time, and the faster your fortune is likely to grow. But just how much? Well, it turns out that this problem was addressed in 1956 by Kelly, working for Bell Labs. It was a problem in information theory, and Kelly basically came up with the optimal way to bet in circumstances like this, if you know the odds, right? Okay, so that would mean if you really knew what fraction of the cards were for Alice and what fraction were for Bob, you could figure out how to bet in order to grow your bankroll as quickly as possible and stop the audit as quickly as possible. Problem is you don't generally know. If you knew exactly what that answer was, you'd already know whether Alice won, right? Okay, so the strategies for, so you need something that's actually going to be able to either adapt, and either you're going to pick something and it's probably not going to be optimal, or you could hedge your bets, no pun intended, and say, well, if the reported results are right, this would be the optimal way to bet, but I want my method to be flexible and adapt to the data if I start to see that my initial odds were actually wrong. And it turns out that there are ways to kind of start with nothing, start with no information, and build up something that performs optimally. And this goes into portfolio theory. So there's a paper by Tom Cover from, was this 1991, that was basically, if you know nothing about what the odds are, what's the best way to proceed? And you can do almost as well as you could if you knew what the odds were going in. And then there's things where this has been adapted to this problem of betting in order to test statistical hypotheses, which is this thing that I've tried to walk you into gently. And that paper, the alpha paper that I just flashed up before, does something like, why don't we start with the reported results and bet as if the reported results are correct, but gradually learn what the proportion of votes for Alice is as we go along and adjust that a bet over time. So it's a shrinkage, a way of shrinking towards what you think is right. So Abraham Wald got there first in 1945, I think. Yeah, this paper was published in 45. Without using the betting language, without using any of these other things, even without using the notion of martingales that go back to Jeanville and 6 years before that, he developed a way of sequentially testing statistical hypotheses. He developed this as part of the war effort, and it was seen as so valuable that he wasn't allowed to publish it until the war was over. So this was an optimal way of testing hypotheses using this kind of a thing where you're trying to minimize the number of samples you have to draw in order to come to a reliable conclusion. All right, so far we've been talking about ballot polling audits where what you poll is, where the numbers in the lists come just from the votes on the ballots. And I want to try to convince you that we can think about comparison audits in exactly the same way, but the numbers in the list come not just from the numbers on the ballots, but also from a reference number, okay? And that reference number could come from anywhere. So that reference number could come from a cast vote record, it could come from batch subtotals, or you could literally make it up. It doesn't matter. What matters is that it's immutable, that you have to commit to it before the audit starts, that if I pull ballot 17, the reference number for ballot 17 is 0.6239, all right? You need to commit to that ahead of time. And we're going to assume that if you take the average of the reference numbers, the average of the reference numbers is bigger than a half. So sort of according to the reference numbers, Alice really beat Bob. Okay. All right, so let's suppose that the average of these reference numbers is bigger than a half. And I'm going to call something the reported margin. The reported margin is going to be take the reported average of those reference values, subtract it from a half. So that's sort of the amount by which Alice got more than 50% of the votes. And I'm going to double that. That's like the spread between Alice and Bob. It's kind of like we would normally think of as the margin. If there were no non-votes, that would just be the spread between Alice and Bob as a percentage. Okay, so I want to take you through 4 lines of high school algebra to show you basically how comparison audits, ballot level comparison audits work, and this is how the one audit method works, and this is the way that you can do hybrid audits if you have a mixture of cast vote records for some cards, but only batch level results for other cards. So let's suppose that the original average is bigger than a half. I want to find another condition that involves the average of the reported list that's an equivalent condition and explain why this kind of works. So what I'm going to do is I'm going to subtract both sides of this inequality from the reported average. So if this is bigger than that, then subtracting that from this is going to be less than subtracting that from the same thing. Right? So far, so good? Subtract a bigger thing, you get something smaller. Right? Okay. The reported average minus a half is exactly this reported margin, but divided by 2. All right? So I'm going to subtract both of these things from 1. And again, because if I subtract something smaller from this, it should be bigger than if I subtract something bigger from the same thing. So this should follow directly from that. And now I'm basically just going to divide both sides by twice this thing. So if I divide that by twice itself, I get a half. And if I divide this by twice that, that's what it looks like. Okay? So this is an equivalent way of saying that the original average was bigger than a half. It's exactly equivalent to that. But now it's expressed in terms of a different list of numbers. Hello? What have I done? All right, so instead of the numbers in the list just being the votes, like Alice is encoded as 1, Bob is encoded as 0, the numbers in this new list I'm going to look at are 1 minus whatever the reported value was for that card. This might come from the cast vote record, minus what the original value was. That would be like 1 if it was a vote for Alice on the card, divided by twice the reported margin. So I know the reported margin before the audit starts. I know the reported value before the audit starts, but I don't know this. But if I pull the card, I do know that, and so I can figure out what the value is that goes with that card, what the list entries that goes with that card. So each one of these numbers, right, the reported value minus the original value, the biggest the reported value could be is 1, the biggest the original value could be is 1, the smallest this numerator could be is 0. Right? And the biggest this numerator could be is 2, right? So this is another list, another bounded list. It's a list of non-negative numbers. I have a known upper bound, et cetera, and I can play exactly the same gambling game as before, where I bet on what the next card is going to be. If the number is bigger than a half, I get b times the amount by which it's bigger than a half. If it's less than a half, I get b times the amount by which it's less than a half. It's a game that is going to be stacked against me unless Alice really beat Bob. Right? So we've said before that this kind of way of doing a comparison audit is somehow more efficient than a ballot polling audit is that doesn't use this auxiliary information. And the reason for that is simply that the range of values in this list, suppose that these numbers came from cast vote records, that the reference values came from cast vote records, and suppose the cast vote records were right. Then every element of the list would be the same, right? There'd be no difference between the reported value and the original value. that difference would be 0, and the value of this ratio would be 1 divided by 2 minus the reported margin. Constant number. That's a sure thing bet. I can bet a lot of money and be sure to win every time, and so I don't have to worry about being risk averse, and my audit's over quickly, right? I can bet more, my audit will be over faster. The original list, some of the votes were for Alice, some were for Bob, some bets I win, some bets I lose. The higher the variance is, the less you can afford to bet without risking going broke. So that's the magic. That's what the magic is in comparison audits. It's that the variance of this list of numbers is smaller. Okay, I keep pushing the button and it keeps doing something else. All right, so that's it. You've had the math class, now on to other stuff. You now understand everything there is to know about state-of-the-art audits except how you come up with a list of numbers for other social choice functions, and that's written down. It's pretty straightforward. All right, so there's a misconception that RLAs are tabulation audits. Verified Voting's website says this. A bunch of people say this. RLAs are not tabulation audits. They do not audit whether the tabulation is right. They do not, in general, check the tabulation. They just check who won. So let me give you an example to try to convince you of that. So here's another 8 ballots. And according to the voting machines, ballot 1 showed a vote for Alice, 2 for Alice, et cetera. Bob, and 8 was a non-vote. Okay, suppose that in reality, this vote, what was supposedly for Alice was really for Bob, this was supposedly for Alice was really a non-vote, et cetera, right? So I'm just going to summarize all these things in a little table, if I can get there. According to the machine tally, Alice got 4, Bob got 3. There was 1 non-vote. In reality, Alice got 2, Bob got 1. There were 5 non-votes. Every single ballot was mistabulated. But Alice really won, and an RLA would correctly stop without going to a full hand count, right? It is not checking the tabulation. It's just checking whether Alice won. So statements like we see from some election officials saying, we did an RLA and it proved that no votes were flipped or proved this or that, it doesn't. Okay. All right. There's an explainer video that Verified Voting published that says the way RLAs work is you draw a random sample of ballots and you compare the fraction of votes for the winner in that sample to the fraction of votes that were reported, and if they're close enough, that's a win, and the audit's not. That's not how they work. There's no comparison between the vote shares in the sample to the reported vote shares. It just doesn't work that way. This betting analogy is really spot on how things do work. Namely, if you can show that it's really implausible that anyone but the reported winners won, and it's really implausible because you won a bunch of money betting on the opposite thing, right? Then you're done. It has nothing to do with matching percentages of votes. There are some people who are concerned that RLAs, because they're sampling at random, what happens if all of the errors are in one precinct? And the answer is, RLAs protect you against the worst case. It doesn't matter whether they're all in one precinct, spread out randomly or anything. What matters is, did Alice really win? So if Alice really won, if Alice didn't really win, you have a high probability of catching and correcting that. And another thing that I'm seeing increasingly is people applying RLA procedures to untrustworthy paper trails and saying, well, at least it shows the tabulation was right. Well, as we just showed, it doesn't show the tabulation was right. And it doesn't show that Alice really won. And it's a distraction from doing the work that it takes to get a trustworthy paper trail. So the same effort would be far better spent improving the practices, the regulations, et cetera, around ballot custody, around eligibility, all of the things that you need to do to get a trustworthy paper trail. That's problem 1. Problem 1 is not do a risk limiting audit, right? Okay. Let's see, shall I talk about, this is kind of reminding me to say that those reference values that I mentioned, one way to get the reference values, when we derived that equivalent condition for Alice really winning, that the average of the list was really bigger than a half, that only involves the averages. It doesn't involve whether the comparison between the reference number on a ballot to the actual vote on that ballot, right? if the average is bigger than a half, Alice really won. So I can rewrite the cast vote records. I can shuffle the cast vote records with respect to the ballots. I can take averages of the votes on the cast vote records. It doesn't matter. If the average of the original list was bigger than a half, the average of that list will be bigger than a half. Right? The overstatement is equivalent net, and that's all that matters for correctness. So one of the things this lets you do is if you want to use batch level information but audit at the card level, you can say, okay, this batch supposedly is reported to have 50 votes for Alice and 40 for Bob and 10 non-votes or something like that. So on average, what is that? It's 50 times 1 plus 40 times 0 plus 10 times a half divided by 100, right? And I could give that number to every single card in the batch, and I preserve the overstatement. So if it was right for the original CVRs, it's right for that, right? So I can use that to check. So that's a way to get around. So what's another advantage of this? If you want to do a batch level comparison audit, you need to be able to physically assemble the ballots that correspond to reporting batches. So typically, voting systems can only report things like precinct subtotals. But once you go to a way of conducting elections like having vote centers, the actual ballots that correspond to voters in a particular precinct could be scattered throughout the entire county, right? And this happened in Los Angeles not that long ago, where someone wanted to do a recount of a relatively small contest, only, 100,000 ballots? Somebody remember this story? Sorry? So like 100,000 ballots, and it would have cost a crazy insane amount of money to do it because you had to go into a bunch of batches across the whole county in order to find them, all right? So similarly, if you wanted to recount the votes in that precinct to do a batch level comparison audit, you would have to go find those ballots in order to retrieve them in order to do this. With this approach, you don't, because the reporting, you pull a ballot, you know what batch it belongs to once you look at it, and you know what the reported average was for it, so you know what its reference value is, because the reference value is coming from the average of the reported value. You don't need to assemble the whole thing in order to do this. Okay, there are other wrinkles that come up in real elections. For example, you go to try to find a ballot and you can't find it, or you know that 492 people were eligible to vote in this contest and showed up, but you can only account for 480 ballots. Where were the rest? So there's ways of dealing with that kind of thing that can only increase the measured risk. They work for missing CVRs and things like that. There are, however, key trust assumptions that you can't get around, and the list is actually really pretty short. You need a known upper bound on the number of cards cast in each contest. If you don't have an upper bound, there could be a gazillion ballots hiding somewhere that would change the outcome, right? It should be obvious that you need an upper bound. Without an upper bound, you can't say anything. You need a commitment to a set of card identifiers before the audit starts. You need to be able to say, get me card number 2,719, and that has to mean something, right? So right now, some risk limiting audits are conducted by, if a ballot is selected for retrieval, it's like, oh, go get the 17th ballot in the batch labeled blah, blah, blah. That's not an immutable identifier, right? It's much, much better to print identifiers on the ballots, and there are ways of doing that that will still preserve the privacy of the voter, and that's another paper. That was the none such paper that I flashed up there before. But it's really important that there be an indelible, immutable mark on the ballot. Otherwise, people observing the ballot won't know whether the auditors retrieved the ballot they were supposed to have retrieved. Okay? Now, it turns out that you don't need trust assumptions about whether the identifiers that were committed to were really the identifiers that were used. It actually turns out that it's okay if they reused identifiers, used different identifiers, didn't identify all the ballots. You can sort of only fail up. You can't fail down. All it can cause you to do is do a hand count that you didn't otherwise need to do. It can't undermine the risk limit. All right. Okay. Again, this thing that I mentioned before, it pains me deeply to see RLAs used as disinformation to put a fig leaf over poorly run elections. That happened in Georgia not that long ago. Here's a paper about that, and I'm not going to go into that in any depth. And this is Ron and me in Napa County in 2009, I believe, auditing contest. The dice there, let me see if I can blow this up a little bit. Ron gave me those dice. They're a treasured possession. You'll notice that they're translucent, not opaque. That's a security feature. If somebody loaded them, they have to load them with something that has the same optical index of refraction as the surrounding lucite or whatever they are that's made out of. Anyway, thank you very much. David's reminding me that I will do a demo of a participatory demonstration of a risk limiting audit in the other room, a few minutes after 5. So we'll have some fake ballots and some dice, and we'll audit an election. Yeah.
So we're going to describe. Hold on.
I'm hard of hearing too, so I'm going to put these.
So if you were to explain to the public in a few sentences, where you wanted them to be able to understand this without going into the math, why RLA proves that an election system is accurate, how would you state that?
First of all, it doesn't prove that the election system is accurate.
Right.
The best thing it does is provide convincing evidence that the reported winners really won, even if the system failed. And the way it does it is, again, it's this betting thing. So first of all, you need a trustworthy paper trail, and it needs to be well organized so that you can sample from it. But you're basically playing this casino game involving the ballots, and you don't stop unless you make a bunch of money on a bunch of bets, at least one of which would have been a loser if the reported winners hadn't won. I mean, you're playing the odds, but if you make $1,000, there's only a 0.1% chance that would have happened.
So then the second question is, why not just count every ballot? Why not just count every one of them and go through this process?
Purely time. Yep. It's just it's really all about efficiency. It's the fact that, I mean, as I demonstrated for that Orange County example, they could have audited every contest in all 190 something or 200 something by looking at less than 1% of the ballots overall. That's a lot less work than a full hand recount of 200 and some odd contests. Yeah. It's purely efficiency.
How many states are doing this?
How many states are doing this? Yeah, approximately 0. Some are doing large portions of this. Some are pretending to do it. Some have laws that authorize them to do it but aren't doing it. There's a lot of variability. Yeah.
When you talk about the importance of the ballot identifier, so when you're doing your RLA, you can request a specific ballot and get it back. For the people that attempt this, or maybe in your ideal world, would you actually physically go pull that ballot, inspect it, and then use the results of that in the RLA, or would you take the digital recorded value?
No. This is you look at the paper. The paper is the evidence, as Ron was saying. Yeah, it's eyeballs on paper. And one of the nice things about this is maybe partly answering the why not do a full hand count. It's a whole lot easier to count to 1 than it is to count to 1,000,000. And it's sort of like, who does this show a vote for? Is it a vote for Alice or not? Right? Everybody agree? Yes, great. Okay. But yeah, it's eyeballs on paper, and there's a lot of reasons for that. So one is, first of all, digital images are malleable. Scan capture, there's computers in scanners, there's computers in SLRs these days, right? There's computers in all kinds of things. How do you know that you have exactly one image of every ballot? That's a really serious issue. And the most common large error I've seen in elections is failing to scan a batch or scanning a batch more than once. That would not be detected typically from an image-based audit. You really need to be sampling the paper. You shouldn't be trusting the computer to tell you how much paper you have. You should have a physical inventory of the paper. That's the whole ballot accounting, poll book reconciliation, all of that stuff is an important part of the security of the paper trail.
Okay. My follow-up is, does the selection process need to be done per contest or simply per ballot?
So the most efficient methods are using something that Ron has worked on a lot called consistent sampling, that lets you draw a sample in such a way that even though these contests overlap in geography, some cards have more than one contest on them, that makes sure that you get enough cards from every contest to have won enough money betting against, betting on the winners in every contest to be able to stop. So there's ways to coordinate this that end up being, they're not uniform sampling across every card. They sample, for contests that have smaller margins, you typically have to look at more in order to win more money, et cetera. So it's, it's not the state of the art for efficiency is non-uniform sampling. All right, I should get out of the way for the next talk. Thank you all for your attention. Oh, is there a question? Yeah.
Are there any issues with achieving true randomization, like just pulling numbers out of a hat? Does that work for like batch boxes or whatever, or does there need to be a more robust procedure?
So right now, the question is like, how do you get good randomness? How do you know that you're not being cheated by whoever's wanting to give you random numbers? So state of the art right now is typically a ritual where something like 20 10-sided dice get rolled to generate a lot of randomness to use as a seed. And then you use a pseudo-random number generator that's very high quality. Right now, one based on the SHA-256 hash function in sort of counter mode. So starting with that as a seed, you either increment the seed by one, and that gives you, if you could tell that that isn't random, you'd have a career in cryptography. There's also nothing to stop you from using genuine randomness to select every ballot. It's just time consuming. Right.
White versus blue noise randomization. In other words, true randomization assumes that there's no structure to the underlying thing that you're sampling, whereas there is structure to elections, and it would be nice to kind of evenly distribute the random. And that's blue noise versus the white noise. Has that been considered?
Well, what we're trying to do is get a uniform sample from each contest, but different contests get different sampling rates, because contests that are sort of smaller margin typically will end up needing a larger sample to confirm them. So if you want to think of this as colored noise, I mean, in some sense it is that, but over each domain of interest, over each contest, it's uniform.
But like if you do batch sampling, a lot of times with this type of truly random sampling, you'll have clumps of samples, whereas with blue noise, it kind of distributes.
The kind I'm talking about is sampling at the level of ballots, not sampling at the level of precincts. There are RLA methods that do involve sampling at the level of batches or precincts. You can either sample those uniformly, or you can sample them with probability proportional to their size, how many votes they have. There are things related to how much error they can contain, which depends on the reported votes. There are ways of doing this in such a way that you maintain the property that if the outcome is wrong, you have a big probability of doing a full hand count.
Fair enough, thanks.
Thank you.